Welcome to the flock! Let's dive into drawing complete reaction diagrams, including this thing called EA, which is also known as activation energy. Stick around to see how it's done. When you're given a reaction diagram just like this one, you're always going to have that potential energy on the y-axis, also known as the delta H over here, and you're going to have the reaction progress on the x-axis. Whenever we end up with reactants that are higher in energy than the products are, we know that the products have formed a more stable bond. And if they're more stable, we also know that those bonds are stronger. And because they're stronger on the product side, we know that somewhere heat must have been released in this reaction. If heat is released, and we know that there's a negative delta H value because this is a slope downwards, then we know that this graph is representing an exothermic reaction. Remember, my little shortcut for this is if I can draw an X from reactants to products just like that, I know it's exothermic. Okay, that's great and all, but what about this hump thing right here? What the heck is that hump? That hump is literally representing the energy it takes for this reaction to go from reactants to products. It's not just a smooth process. We have to actually overcome an energy barrier just to get from the reactants to the products. And we call that barrier the activation energy. We represent this distance between the reactants and the top of the hump as literally EA, and that stands for energy of activation. So obviously, if you end up with different chemical reactions, they're all going to actually have a different energy barrier to get from reactants to products. In some cases, your chemical reaction is going to have a really big hump. It's going to have a lot of energy to overcome just to get from the reactants to the products, to actually get the reaction started. Whereas other chemical reactions might have a tiny EA, and it happens really fast on its own. Just as a reminder here, all reactions do involve the breaking and making of bonds. Energy is required to break the bonds. You have to put energy in to break bonds, and that's where our endothermic reactions lie. And if we have more energy released or left over after the new bonds have reformed, we have what we call an exothermic reaction. So it's basically dependent on how much energy did we have to put in versus how much energy would we get out for it being endothermic or exothermic. Either way, we know that bonds are going to always be broken and reformed in any chemical reaction. So back to the initial problem we started with. If we were going to draw a complete reaction diagram for the following chemical reaction, which we recognize is a combustion reaction because it has methane and oxygen reacting to form carbon dioxide and water, that setup is always indicative of combustion, and we also see the delta H, which we calculated in a previous video, is a negative value. So we know that to draw this reaction diagram, we're already dealing with an exothermic reaction, just based off of our first observations. We're gonna need to draw a y-axis labeled as potential energy or delta H. Those two things are synonymous in this case. And an x-axis labeled with reaction progress. I'm going to represent that as RXN. That's a pretty common shorthand for reaction. And then we need to draw this as an exothermic plot where our reactants are going to be higher in potential energy than our products. So our products are going to be more stable, stronger bonds. Of course, we know what our reactants are. They happen to be CH4 and oxygen. So we might as well label that. And our products happen to also be CO2 and water. So we're going to label that as well. We know that the distance between the reactants and the products is literally our delta H, and our delta H is equivalent to negative 808 kilojoules per mole, which again we calculated in a previous video using Hess's law, which is the sum of the products minus the sum of the reactants. But now we need to draw a complete reaction diagram where we're also taking into account this activation energy mumbo jumbo. We need to draw in a hump or a reaction progress line from the reactants to products. It's not just going to be like this, because that would imply that there's literally no energy barrier to get from the reactants to the products. We need to draw in a hump. Now that hump size is arbitrary. You may have drawn it up like this, you may have drawn it a little lower. That doesn't matter because we don't currently have a value for EA. We do still need to symbolize that EA is present by including the hump. but we don't know how big it is, and that's okay for now. Now that you've seen me try it, go ahead and pause the video here and see if you can draw the complete reaction diagram for this chemical reaction. But first, you're going to have to use Hess's law to calculate the delta H of the reaction using these values. Go ahead and pause the video now before I show you how to do the answer. If you calculated for the delta H of the reaction using Hess's law, you would have taken the value for water in its gaseous state, negative 241.8, and multiplied that by 2 to give you a final delta H of reaction value at negative 483.6 kilojoules per mole. Products minus reactants means that we have product side minus the reactant side, which is already 0. For Hess's law, we're going to take the sum of our products, which is negative 483.6, and subtract that from the sum of our reactants, which was just 0 because they're both in our standard state. So our delta H of a reaction is literally just negative 483.6 kilojoules per mole. And now for the reaction diagram. If you drew something that looked like that, you got it right. Pat on the back. Okay, so we said this EA, this hump, is an energy barrier. That means it slows down a reaction. Sometimes it slows down a reaction by millions of years. Not even kidding here. So how are we going to combat that energy barrier? How are we going to combat the hump? That's where catalysts come into play. No, not catalyst. Catalyst. A catalyst is something you add to the chemical reaction and it speeds up the process by lowering the activation energy hump. But most importantly, it doesn't get used up in the reaction. It's not really involved in the chemical reaction itself. It's kind of like a coach on the sidelines cheering on the football team. Go, 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 go faster, run faster, quarterback. I don't know. I'm not very familiar with football terms, but whatever. You wouldn't dare see the coach actually in the game. It's not actually in the chemical reaction, but he's cheering on the reaction. Go! Some examples of catalysts include enzymes like the ones in your body that help you live and for the cells in your body to actually undergo mitosis and copy your DNA. A lot of those tend to end in ACE, like DNA polymer ACE. Anything that ends in that ACE is typically an enzyme, a catalyst. Or if you've ever heard of this thing called a catalytic converter in your automobile, that's using catalysts, hence catalytic. There are many chemicals that can be catalysts. Potassium permanganate, yeast, sodium iodide, potassium iodide. The latter three we will see in a demo to follow. Hang tight. So what if we took that same exact chemical reaction we started with and we added a catalyst to it? How would this hump change? What would happen to that activation energy? We would literally depict that as a smaller hump. Now, how much smaller? Arbitrary, unless they give you an actual value that you're going to measure along the y-axis. But in this case, the main idea here is that you just want to draw a smaller hump, indicating that it was catalyzed and the reaction happened faster and you didn't have to wait like a million years for it to actually happen. So you're likely going to see this depicted on a full reaction diagram as follows. You're going to have something like this where there's a little symbol like that at the top of the hump with cat, and that means that it was literally catalyzed. You inserted a coach into the chemical reaction to cheer it on. Go faster! But remember, it didn't get used up in the reaction. Notice that this purple hump is much smaller than the red counterpart hump, because the red counterpart hump up here is uncat, meaning it is uncatalyzed. It did not have a catalyst added to it, meaning that that reaction took way longer. Because remember, catalysts speed up a reaction. They make it happen faster. So as promised, here is the demo. The demo is this. We have hydrogen peroxide, and if you leave that alone just by itself over time, hydrogen peroxide decomposes or breaks apart into oxygen gas and liquid water. So if you were to leave your hydrogen peroxide at home uncapped, eventually it would not be hydrogen peroxide anymore because it decomposes. This process takes a long time if you were planning on just sitting there and watching it happen. However, if we add a catalyst, i.e. yeast, this reaction will happen much faster because our reaction diagram will have less activation energy to go from peroxide to oxygen and water. So the cool part about that is that if we add some soap, and speed up the reaction with the yeast, will essentially capture all of these oxygen gas bubbles and create lots of little tiny soap bubbles making foam. So as I show you this reaction demo, I want you to think about what the catalyst is doing to the reaction rate of the decomposition of hydrogen peroxide and whether or not this reaction is exothermic or endothermic based on your observations. Let's check it out. Watching hydrogen peroxide decompose into hydrogen gas and oxygen gas is so boring. So let's speed it up with a catalyst. We're going to use soap to capture one of the products, oxygen. And everything in life is better with color, so let's add blue. And now for the thing that'll speed this reaction up, the yeast catalyst. Prepare for bubbles. So how is this reaction possible? Well, hydrogen peroxide, H2O2, decomposes over a long period of time into O2 gas, all on its own. But when we add the catalyst, the yeast, it speeds up the reaction by lowering the activation energy hump and thereby making the reaction happen much faster. So instead of waiting for eternity for the hydrogen peroxide to turn into O2 gas, we can capture all those gases using the soap and the catalyst to speed it up and make foam. Chickadee, check yourself before you wreck yourself. Make sure you can answer these questions before you move on to the next concept. Catalysts blank the activation energy of a reaction, thereby making the reaction happen at a blank rate. Then, using the following delta H's of formation, calculate the entire delta H of the reaction for the reverse of photosynthesis, and draw the complete reaction diagram for that setup, including what would happen if you added a catalyst. Make sure you label everything accordingly, of course. In this lesson, we went over how to draw a complete reaction diagram, including EA, or activation energy. We then talked about how we can take that activation energy and lessen the energy barrier by adding a catalyst. No, not lisp, catalyst. And a catalyst is something that speeds up the chemical reaction. Remember the coach on the sidelines going, "Go, you can do it, go faster," but doesn't get used up in the chemical reaction. You wouldn't see the coach in the actual NFL football game now, would ya? No, of course not. Coach Catalyst stays out of the reaction, but speeds it up. We then talked about how you can show that on a complete reaction diagram by drawing a smaller EA hump when it is catalyzed, and you symbolize that with that symbol and cat for catalyzed, or this symbol and uncat for uncatalyzed. Oh, and we also briefly went over how to use Hess's law to calculate the delta H of a reaction and plot that on our complete reaction diagram. Please give this video a quacks up, and when you're out of luck in chemistry, subscribe to the Duck.
No ducks, no glory.